Now that we have an example to think about, let's define some key ideas and some key terms here. So first, to manipulate the matrix to get to each next step, okay, we are doing some operations on these rows, right? For example, right here, we are taking a row and adding to it a multiple of a different row, right? Here, we're multiplying a row by a constant. These are examples of row operations. There are certain row operations we can perform and still keep the system we get equivalent to the original system of equations. We call these row operations elementary row operations. And we have three elementary row operations. We can switch the order of two rows. We can multiply a row by a non-zero constant. And we can add a multiple of one row to another row. And let me just illustrate what these would look like symbolically. Okay, multiply a row by a non-zero constant. So we saw an example of that. That could be like if I want to change the ith row, I can multiply it by some non-zero constant k and store the result in row I. Okay, if I want to switch the order of two rows, say I want to switch the order of rows I and j, symbolically I can write Ri and then I swap it with row j. Okay, and add a multiple of one row to another row. So I could do, say, some constant times row j. I could add it to row I, and that's my new row I. Okay, we saw both of these elementary row operations in the last example. We didn't see this one, but that one's pretty clear that it's not going to change the solutions to the system of equations, right? So let me just show you these two. So here we're multiplying a row by a non-zero constant, right? In this case, the non-zero constant's half. And then in both of these, we add a multiple of one row to another row and store it in that second row, okay? So each one of these preserves the solution to the system. Performing an elementary row operation results in a system of linear equations equivalent to the original system. That is, the two systems have the same solutions. And it doesn't take too much to convince yourselves of that fact. Remember the rows here, they are the equations of the system. So if I were to say swap these two rows, well, obviously that would not change the solution to the system of equations, right? So first one checks out. Does not change the solution to the system. What about multiplying a row by a non-zero constant? So that would be equivalent to multiplying both sides of an equation by a constant. And that's something we already know. So for example, if I multiply both sides of this equation by 5, the solutions to the equation are the same. The equation really hasn't changed at all, right? Notice it does have to be a non-zero constant. If I multiply both sides of the equation by 0, then I get the equation 0 equals 0. And while 0 does equal 0, I have lost all the information that is held in that equation. So you don't want to multiply by 0. You will lose information. Okay? And add a multiple of one row to another row. This one's the trickiest one. If I add a multiple of one row to another row, like I did here, right? R2 minus 4 times R1, R3 plus 1 times R1. Because I am adding an equation, I am adding, say, R3 plus R1. I'm adding this side of equation 1 to equation 3. I'm adding the right side of equation 1 to the right side of equation 3. And because equation 1, the left and the right side are equal, I'm really adding the same thing to both sides, right? They just look different. And so the quality is preserved and the characteristics of the equation are preserved. Okay? So each one of these, if I apply these elementary row operations, it preserves the solution. And so the idea is, these are my tools, okay? This is my tool bag. These are the tools I have to manipulate a system of equations and to get it into a form that's easier to work with. And that's what we're doing here. When we apply these elementary row operations, we change this into this. Or in matrix form, we change this into this. Two ways to describe the same change. Okay, and we saw that this was much easier to work with. We could solve this using back substitution. So using these tools, we can change a system of equations that's hard to work with into a system of equations that has the same solution, but is easier to work with. Okay, in this case, what we saw is if we keep on changing it, we're able to change our original system into this, or into the system x equals 1/2, y equals negative 13/2, z equals 2. And it's very easy to see the solution of this system, right? And so that's the goal of these elementary row operations. We want to change a system that's difficult to work with into one that's easier to work with.